Yo, 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 Math by the Moon back with another video today. What I'm going to hit you with today, some expanding and condensing log properties, a little bit of change of base theorem, and then an application with decibels. So all you guys out there with your big subwoofers, this will help you out, at least understand where those numbers come from. So let's get after it. You ready? Ooh! So the first thing I want to show you would be your log properties, and the log properties look like, let me find my desktop. Log properties look like this right here. So we've already been through these, so if you want to pause the video and jot these down if you didn't already do so in Edgenuity, and I'll be referring to them quite a bit as we go throughout. We always know that the logs are meant to do questions that involve exponents, and so we have to reverse the idea of what exponent properties are. So when you have multiplication with like bases, you add exponents. So now we're reversing that. So multiplication means we could expand this by addition. Division, same principle here. So when we divide with like bases, we subtract exponents. So when we expand with the quotient rule, division turns into subtraction. The power rule, when we raise something to a higher power, we multiply the exponents. So this power becomes the coefficient of which we multiply the log of. The change of base rule, this is a way to do calculations back before the calculator could actually do any log base other than 10 or E. So remember, common log is base 10 and natural log is ln, and those are buttons right on your calculator. So if you wanted to do some evaluations, you can actually use this change of base theorem to do it base 10 as opposed to base B, which is nice. And years and years and years ago, before the calculator, there was tables of answers for anything base 10, so you could do the division by hand if you had to. So that's the purpose of the change of base rule. And so if we look at a problem that requires us to expand, what we'll be doing is we'll be taking something that's in condensed form, which is a single log, to multiple logarithms based on these properties. And the opposite's also true. If we're looking to take something and condense it, we're looking to having a bunch of logs and ratchet it down into one single log of a common base, of the same base, whatever that might be. So here's our first couple of problems. I kept the first one few simple here. So what you want to do is you want to figure out how many, I always say pieces in class, but it's literally factors you have in this problem, and that's going to determine how many logs you're going to create. So what we have is we have a multiplication in between the 3 and the x plus 2. So multiplication turns into addition. So we're going to split this up into 2 logs because we have 2 factors. We have a factor of 3 and a factor of x plus 2. So it's log base 4 of 3 plus log base 4 of x plus 2. So there's our expanded version. That's as expanded as you can get. Down here we have 1, 2, 3 pieces to this puzzle. Factors. All factors are separated by multiplication or divisions, which is why I didn't count this as 3 right here. I just counted it as a single binomial factor. So what I would do in this one is I would have log base 5 of 3, and we know that division turns into subtraction of a product here, right? A product here. So we're going to have addition in between these 2 logs. So it's going to be log base 5 of 4 and log base 5 of w. Now, the key to that one is really easy. You might not notice it, but I put that entire denominator in parentheses, signifying that it is part of the entire denominator. Meaning if I were to distribute this negative sign, it would really be minus log base 5 of 4, but also minus log base 5 of w. So you might see it written like that. And in my class, what I would talk to you about consistently is how these are both in the denominator. So you could imagine that as being like a negative exponent. So these are both like 4 to the negative 1 and w to the negative 1. And remember that exponent property drops that exponent down in front of the log. So that's why you get that minus sign in front. And in class, I work out an entire example like that. But if you've already seen it, which most of you have, you get it. So if they're in the denominator, they get a negative sign in front of the log. So let's go the opposite direction now. Let's condense. So I see that we have two things here. We have subtraction in between. And what we're going to do is we're going to turn it into one condensed log. They're both common logs. So I'm going to have one log, base 10, which we don't have to really write here. Subtraction turns into division, so I'm going to put the bar in. And the first log of 5 is going to be in the numerator, because if you think about what I just said, that's a positive 1 right there, right? Right, so that's going to be a positive exponent, meaning that it would be in the numerator. And then this would actually be a negative 1 if I put that back. So that's going to be x minus 3 in the denominator. So I guess a lot of kids got good at this because they would see that anything that has a positive leading coefficient goes in the numerator, anything with a negative coefficient goes in the denominator. And that's how it would look when you're done with it. So a little more complicated version down here, we got powers we have to put back first. Okay, so think of your PEMDAS, please excuse my dear Aunt Sally. And remember that if you were to do the order of operations, you would start with parentheses, then move on to exponents and so on and so forth, PEMDAS. So really, we don't have any parentheses to put back in this type of problem, but we do have an exponent, a power we want to put back. So let's put the powers back first. A lot of times you'll see people draw these little arrows right here, signifying that they'll go back. So it'll be the log, common log again, base 10 of x to the 1/2 minus the log base 10 common log of y to the 3rd. Whoops, almost put that 3 on the outside, should be on the inside. Now, you'll remember that the x to the 1/2 is the same as the square root. And also subtraction means that this y cubed is really in the denominator if we were to condense it up. So our final look on this will be log, common log, square root of x over y cubed. That's what it would look like condensed. Again, subtraction turns into division. Okay, change of base theorem. Let's go out here to the change of base theorem and maybe a decimal application if we have time here. So the change of base theorem, like I said in the beginning, in the opening, was so that we could come up with a value or an approximation for these questions that we really don't know. This is 4 to some power equals 9. So all we really know is 4 to the 1 is 4, 4 to the 2 is 16. It's somewhere in between there. And if I had to guess, I'd say it's pretty darn close to 1.5. I don't know. But what the change of base theorem does is it says if you take the log of 9, common log of 9, divided by the common log of 4, and this becomes something you can just type into your calculator because the calculator has the common log over here on the side. Bang that in. 1.585, 1.585 is approximate. And that's your change of base. In Edgenuity, they do some application problems, which are kind of cool because they intertwine here the rules for logs, but also an application where it's used in the real world. So in addition to like earthquakes, decibels, sound is another logarithmic application. So this is the formula for the decibels that you're hearing out. And so if you had like a decibel reader, it would read in L is the letter for that, and that's in decibels. The formula is 10 times the log, common log of I over I sub 0, where I sub 0 is the lowest human intensity we could pick up. It's a frequency. Frequency in watts per square meter. That's what this is in. So 10 to the negative 12 is kind of a constant or an approximation of a constant for most humans. As you know, dogs can hear different pitches than humans can. So we're going to substitute 10 to the negative 12 right in there. And then let's say the problem gives us a frequency of 10 to the negative 8. I think they use like a lawnmower in the one. In my opening, I talked about stereo speakers. Like if you have like a stereo competition, that was big back in my day, and I'm an old fart, but so they would measure it in decibels. So let's just substitute, let's say something making a noise of 10 to the negative 8 frequency, and our lowest base ability to hear is 10 to the negative 12. So what that looks like is 10 log of 10 to the negative 8 over 10 to the negative 12. And if you remember your negative exponent rules, we can switch the negatives around here since they're negative exponents, and that's going to really be 12 on top and 8 on bottom, which means we'd have 10 to the 4th, right? So 10 log of 10 to the 4th. Now, using your common log here, you know that log of 10 to the 4th is 4, right? Because the base 10, 10 to what power gets you 10 to the 4th? Well, 4. 4 times 10 would be 40 decibels. So that would have been your answer for that, okay? And they do ask you to do a comparison, like a ratio between two values. So you'd have to get like this one and then another one and then divide it out. So watch out for that. If you have any questions on expanding or condensing, hit me up. Gladly jump on a Zoom and help you. All right, later.